In this class, we'll see the convolutional integral with help of graphical method. Last class, we have seen convolutional integral with help of mathematical method and also with help of Laplace transform. Again, before going to this, we made some mistakes in the previous classes. Still correct it, then later will come. Yeah. Okay, so while solving this problem, okay, see for this problem, we had some confusion here because as the limit goes from 0 to t plus 3, again t could be anything, t could be infinite also. But what could be the lower limit? That we had confusion here whether to put u of t, because u of t means it varies from 0 to t plus 3. So now this is not u of t, this is u of t plus 3. Okay, u of t plus 3. That means what? This expression is valid from minus 3 to infinite, because u of t plus 3 means what? It is starting at t is equal to minus 3 and goes up to infinite. Okay, so this expression is valid from minus 3 to infinite. Or if you have a confusion here, from here we can conclude this, because for the first signal, what is the limit? It goes from 0 to infinite. For the second signal, okay, again this is e power minus 3t, so it comes like this. Okay, it is exponential decay, so it comes like this. Okay, then the second signal is u of t plus 3, then it goes like this. Okay, it starts at minus 3 then goes up to infinite. Again, we know that what is the lower limit? Lower limit is the addition of lower limit, that is 0 minus 3, so that minus 3 is the lower limit. Then what is the upper limit? Addition of upper limits, that is infinite plus infinite, so plus infinite. So that means what? The final expression is valid from minus 3 to infinite. The final expression is valid from minus 3 to infinite, that we can easily denote with u of t plus 3. Okay, so same thing, we got confusion in even in Laplace transform. Okay, here already we are having expression y1 of t. Again, to apply this e power 3s, we have to replace t with t plus 3. But we have replaced in this expression, but we have not done it in u of t, but we have to do in u of t also. So u of t plus 3. Okay, again this expression is valid from t is equal to minus 3. We find the convolution of x of t with h of t with the graphical method. Again, for simplicity, I have taken two signals with the same duration. Okay, already we have solved this problem with help of mathematical method and also with help of Laplace transform. Now we'll try with graphical method. Again, this graphical method only you will be using in the examination. Okay, then what is the formula of the convolution? Y of t is equal to x of t convolution with h of t. Okay, then integral minus infinite to plus infinite x of tau h of t minus tau d tau. Okay, first now we'll try to find x of tau from x of t, then h of t minus tau from h of t. Then later graphically we'll do the analysis, then we'll find the integration. Okay, first of all, what is x of tau? X of tau is simply replace the variable to t with respect to tau, so that you'll get the same shape. But now the variable is not t, the variable is tau. Okay, and originally the variable is t, but in this formula the variable is tau. Okay, so we got x of tau from x of t. Okay, just to replace the variable. And then we cannot get directly h of t minus tau. Okay, what is the procedure? I already told you. From h of t, you have to find out h of tau. From h of tau, you have to find out h of minus tau. From h of minus tau, you have to find out h of t minus tau. This is the procedure. Okay, so already we have h of t. Okay, then what is h of minus t? Okay, what is h of minus, sorry, what is h of tau? Okay, h of tau, simply replace the variable, and again here also it is going from 0 to 2, 0 to 2. Okay, then from this I'll try to find out h of minus tau. Okay, again mirror image with respect to y-axis. Okay, so this is minus 2, 0, and 1. This is h of minus tau. Okay, h of minus tau. Okay, from this we'll try to find out h of t minus tau. Okay, so finally h of t minus tau. So that means what, already h of minus tau is there. You just add t everywhere. Okay. So anyway, the shape will be this one. If you add t with 0, you'll be getting t here. If you add t with minus 2, you'll be getting minus t, minus 2 plus t. Okay, so now this is x of this is h of t minus tau. Now I will not be putting this axis now. Why? Because the axis actually indicates 0, okay, this central axis. But if I put here the central axis, that means I am telling that, suppose if I put the central axis here, that means I am trying to tell t is always greater than 0, but that is not so. T could be anything. T may be greater than 0 or t may be less than 0. Okay, t could be anything. Okay, we have to analyze for both t as a positive and t as a negative. Okay, that's why, to avoid that confusion, I will not put this axis here, because here the ambiguity here is t. We do not know what is the value of t. It could be positive or negative. So that simply I will put this shape without central axis. Okay. Up to this point, we can put the central axis. But once if you define h of t minus tau, we cannot. Okay. Don't put the central axis. If you put that again, it will make confusion. Okay, so now we know h of tau. We know h of t minus tau. Just I'll write it in the next page. Then we'll do the analysis. This is x of tau goes from 0 to 2. Then what about h of t minus tau? Its shape is like this, but it goes from minus 2 plus t, minus 2 plus t to plus t. Okay, minus 2 plus t to plus t. Okay, now what we are doing, we are multiplying x of tau with h of t minus tau. That is the first procedure. Once if you know x of tau and h of t minus tau separately, then you have to multiply. Okay, so when you multiply, if both are having value, then only you will get value here. If one is having value, another one is not having value, again, then also you will get 0. If both are not having value, then also you will get 0. So now we'll do this multiplication graphically. We'll do this multiplication graphically. So just we'll multiply these two graphically, because we do not know what is the value of t. That is the main problem here. T could be anything. T could be negative, or t could be 0, or t could be positive. Okay, so we do not know. So now we'll analyze. Okay, so case one, suppose I take this diagram here, 0 to 2. I am drawing this diagram here completely. That means what? Between these two diagram, now there is no overlapping. Anyway, central axis I am trying to put here now. Okay, so just we are analyzing. Okay, just we are going to analyze now. Okay, so now if I take this x of tau here and h of t minus tau here, that means what I am trying to say, t value is less than 0. So in the case one, what I am trying to say, in the case one, what I am trying to say, t value is less than 0. When t value is less than 0, what is actually happening? There is no overlapping. Okay, when t value is less than 0, what is actually happening? Because t could be anything. It could be less than 0. Okay, in this case, we have chosen t as less than 0. In the next case, it may be greater than 0. Okay, again, we also put some cap on here. But once if t is less than 0, definitely minus 2 plus t is also less than 0. Okay, again, graphically, you can visualize here. Okay, if t is less than 0, definitely minus 2 plus t is also less than 0 only. So that's why we'll put simply t less than 0. So there is no overlapping. Once if there is no overlapping, what we'll be getting? Okay, once if there is no overlapping, integral minus infinity to plus infinite, 0, 0, d tau, then answer is 0. Okay, once if there is no overlapping between these two diagram, simply y of t value is 0. Okay, without doing this, directly you can put, definitely it will be 0. But under what condition? Under when t is less than 0. So this is valid only when t is less than 0. Okay, y of t value is 0 only when t is less than 0. Okay, but once if t is greater than 0, again we have to analyze. Okay, so now next one is case 2. Case 2. Now I am going to choose a t such that it provides the partial overlapping. Okay, say x of t is here, 0 to 2, 1, tau space x of tau, then I choose h of t minus tau like this. Okay, this is h of t minus tau, where what is the lower limit? Minus 2 plus t, minus 2 plus t and t. Okay, again, now if you see here, this is the central axis 0. If you see here, there is overlapping. Okay, there is overlapping of this part in both the cases. Okay, what is the overlapping region? From 0 to up to some time t. Again, once if you want to get this overlapping, what is the value of t? Okay, if you want to get partial overlapping, what should be the value of t? If your t value is in between, see, if you choose t in such a way that it is in between 0 to 2, okay, it is in between 0 to 2, okay, then you'll get partial overlapping. Okay, so if t value is, okay, if t value is in between 0 to 2, you'll get the partial overlapping. Okay, because once if t is between 0 to 2, definitely minus 2 plus t will be, again, will be less than 0 only. So again, once if this is fixed properly, again, this will not make any confusion. So now you'll get partial overlapping. Okay, once if t is in between 0 to 2, definitely you will be having partial overlapping. Okay, then what is the answer? Y of t is equal to integral minus infinity to plus infinite x of tau, x of tau, h of t minus tau d tau. Okay, now you are having partial overlapping. Okay, when you have the overlapping, the limit goes from 0 to t. When you go from, again, even though you are having partial overlapping, again, we do not know what is t value. T value could be anything between 0 to 2. So that's why we'll put upper limit as t, but the lower limit is 0, because here also it is starting at 0, here also it is starting at 0. So because in the second diagram you are having value even at negative, but in the first diagram your value starts at 0 only. So that's why the limit starts at 0. Okay, again, in the first diagram, you are having value at up to 2, but we do not know what is the value of t here. That's why the t could be anything. It may be 1 or 2 or any value in between 0 to 2. So that's why we'll put t here. So then now, once if you multiply 1 into 1, then 1 d tau. Okay, so tau t 0, again t, this is valid only when t is from 0 to 2. This is valid only when t is from 0 to 2. Okay, otherwise it's not valid. Okay, okay, only when the time index is from 0 to 2, this t is valid. Okay, next, case 3. Okay, so case 3, case 3 we are getting full overlapping. Case 3 we are getting full overlapping. Okay, again, in this case, how can we get full overlapping? Okay, in this case, how can we get full overlapping? Okay, we are analyzing this with respect to this. When you choose t as 2, we'll get full overlapping. Okay, see, these are all the reference diagram. This is x of tau that goes from 0 to 2, and then what about h of t minus tau? H of t minus tau that goes from minus 2 plus t to t. Okay, when you choose t is equal to 2 exactly, okay, when you choose t is equal to 2, what is happening? You will get exact overlapping. You will get exact overlapping, because once if you put t is equal to here, this is 0, this is 2, then your h of tau comes here. Okay, your h of t minus tau comes here. That means what? You'll get full overlapping. Okay, you'll get full overlapping. So then what's happening? Y of t is equal to integral minus infinity to plus infinite. Okay, integral minus infinity to plus infinite x of tau h of t minus tau d tau. Then what is the limit variation? Limit goes from 0 to 2. Again, both multiply, if you get 1 d tau. Okay, tau 2 minus 0, that is equal to 2, but this is valid only when t is equal to 2. This is valid only when t is equal to 2. Okay, otherwise it's not valid. Okay, only at t is equal to 2, this is valid. Okay, then this case 3. Case 3, again we'll try to get partial overlapping. Again we'll try to get partial overlapping. Okay, actually what is happening here, okay, in general what is happening, we are taking one first reference signal like this from 0 to 2, okay, and then h of t minus tau, in the first case we are trying to put here, then we are getting partial overlapping, then we are trying to put here, we are getting, sorry, this is x of tau. Again, first we are trying to put h of t minus tau here, so no overlapping. Then we try to put here partial overlapping. Again, exactly here, full overlapping. Then we try to put here partial overlapping, then no overlapping. Okay, so we start with no overlapping, then partial overlapping, then full overlapping, then partial overlapping, then no overlapping. So that means what? The second diagram, based on that, where you put the second diagram. Okay, see, second diagram I can put here, I can put here, exactly I can put here, or I can, or I can put partially. See, wait, draw a little bit. See, I can, second diagram I can put here. So now no overlapping. Okay, I can also put here partial overlapping. I can also put here exact overlapping. I can also put here again partial overlapping. Again I can also put here. So again partial overlapping. So based on where you are placing your second signal, that is h of t minus tau, okay, you will be getting no overlapping, again partial overlapping, again full overlapping. Okay, again full overlapping, again partial overlapping, again full overlapping. Sorry, again finally no overlapping. Okay, no overlapping. So this we have verified. First no overlapping. In the second case also we have seen partial overlapping. Third case also we have seen full overlapping. Case 3. Then the next we are at case 4. Okay, so next we have to see partial overlapping. Okay, partial overlap. So now x of t is here. X of t is here 0, 2. Again, this is 1 tau space x of tau. Again, where I am fixing my second signal, I am fixing here. Okay, I am fixing on the right side. Okay, again, what is the variation here? Minus, this is minus 2 plus t. This is t. This is t. Okay, so now to get this condition, what should be my value? So to have a overlapping, partial overlapping here, what should be the limit condition? Okay, how I have to choose the limit? Okay, so my t should be greater than 2. Okay, my t should be, this 2 is for this time index. Okay, my t should be greater than 2. But it doesn't mean that definitely I will get partial overlapping. So I will get partial overlapping only when my t is greater than 2, and also this minus 2 plus t should be less than 2. Okay, see, now this is little bit critical. Okay, I will get partial overlapping only when t is greater than, t is also greater than 2, and also minus 2 plus t is less than 2. Because if you put only condition t is greater than 2, suppose if I choose t is equal to 10, then definitely I will not get any overlapping at all. Okay, I will completely go out of this stage. So that's why when you write the limit here, you have to be a little bit careful. Okay, see, I'll get partial overlapping only when t is also greater than 2, and also minus 2 plus t is less than 2. So minus 2 plus t less than 2 means what? T is less than 4. So that means when I will get the partial overlapping only when t is greater than 2 and t is less than 4. That means this partial overlapping is valid only when t is greater than 2 but it is less than 4. Okay, this partial overlapping is valid only when t is greater than 2 but less than 4. Okay, so now we'll see what happens. And what is the integration? Y of t is equal to integral minus infinity plus infinite x of tau h of t minus tau d tau in integral. Again, from where your overlapping starts, again it starts from here, that means from minus 2 plus t. Okay, again this could be t, but it is ending at here because this second signal is having value, but the first signal is not having value beyond 2. So that's why the upper limit is 2. Again, we do not know minus 2 plus t. Minus 2 plus t could be, it could be here, or it could be here, or it could be anywhere inside this 0 to 2. So that's why the lower limit is minus 2 plus t, but the upper limit is 2. Then 1 into d tau. Okay, then what you are getting, 2 minus 2 plus t. Okay, 2 minus 2 plus 2 minus t, 4 minus t. But this 4 minus t is valid only when the limit is in between 2 to 4. Okay, so we got y of t is equal to 4 minus t, that is valid only when t is from 0, sorry, t is from 2 to 4. T is from 2 to 4. Okay, so now I will consolidate the result. I will write all the result in one page. Now y of t, when we got 0 when t is less than 0, we got 0 when t is less than 0. Okay, then we got t when this is t is in between 0 to 2. Okay, then we got exactly 2 at t is equal to 2. Again we got 4 minus t when 4 minus t when t is in between 2 to 4. Then what happens once if t is greater than 4? Once if t is greater than 4, definitely it is 0. Okay, that also we have to see, but we have not seen it. Okay, see, we'll see that also. Okay, then what is the final case? Again, no overlapping. Okay, no overlapping. That means what? The first diagram is here, 0 to 2, tau space 1. Then second diagram I can choose here. Okay, minus 2 plus t, then t. Okay, minus 2 plus t, then t. Suppose if I choose minus 2 plus t greater than 2, if I choose minus 2 plus t greater than 2, definitely t will be greater than 2. No problem. Okay, there is no doubt at all. Okay, if I choose this limit as greater than 2, definitely this t will be greater than 2. So that's why we no need to write this. Okay, so that means t is greater than 4. Okay, t is greater than 4. When t is greater than 4, what is happening? There is no overlapping. So integration of 0 d tau. So finally 0. This is valid only when t is greater than 4. Okay, so that only we are writing here. So when the limit goes beyond 4, again the value is 0. Okay, see, now we are defining the mathematical function at a different limit. Okay, previously, okay, during the mathematical approach, okay, we got in different way. Okay, we got in different way so that we put plus everywhere. But now this function is defined separately. Okay, the see, t is valid only when 0 to 2. This is valid only at t is equal to 2. This is valid only at 2 to 4. Okay, so now we no need to add. Okay, so we can separately draw the function that will provide the final value of y of t. So you have to understand the difference between the mathematical approach and this approach. In mathematical approach, we added all the value, but we got different limit here and also different mathematics here. But here we no need to add. Okay, because functions defined separately at separate interval. But finally our answer will be same. Okay, so now we'll try to draw this. Final answer. When t is less than 0, again the function is 0. When t is less than 0, the function is 0. This is final answer, y of t. Again, what is happening between 0 to 2? Between 0 to 2, the function value is t. That means with the slope 1, it is increasing linearly. Okay, from 0 to 2, it is increasing linearly. And then what is happening at t is equal to 2? At t is equal to 2, you will get a value of 2. Already you got 2 only, because once if the function increases linearly with the slope 1, when you go to 2 again, definitely you will get 2 only. It's already there. No need to put once again. Okay, so you are getting 2. Just we are cross verifying it. That's it. Okay, the same 2 you can get from here also. Okay, because this function is also valid from 0 to 2. This is valid at t is equal to 2, only 2. Okay, so now what is happening next? From 2 to 4, what is happening? That is following 4 minus t. Okay, so that means what? Suppose once if you go to 3, if you substitute t is equal to 3 here, you will be getting 1. Okay, you will be getting 1. Then once if you go to 4, if you substitute here, you will be getting 0. That means this function will come like this. Okay, so again this is 4. Again, if you see carefully, this is will be of slope minus 1. Okay, again the same answer we got already in the mathematical approach itself. Okay, so same triangular function. Okay, once if you do the convolution of two equal duration rectangular signal, okay, with 0 2 with 0 2, then you will be getting the triangular function. Okay, so now we are getting this answer with the help of the graphical approach, 0, 2, and 4. And also we can verify this AX area and AH area is same as the AY area. Anyway, okay, this same thing we have verified earlier also. So this is the graphical approach. Okay, so during the graphical approach, you have to be very careful. Okay, you have to follow these steps. First, no overlapping, partial overlapping, full overlapping, again partial overlapping, again finally no overlapping. So that means what? You are keeping the first signal, first graph as a standard one, fixed one. Then you are moving, you are sliding. Okay, you are moving or sliding. You slide the h of t minus tau. You slide h of t minus tau. Okay, in this manner. First you keep here, then you go here, then you go here. So that once if you slide from left to right, you will be getting this. Okay, then finally we can get the answer. Okay, so in the beginning, this approach is little bit difficult, but later once if you solve one or two problem, again this will be easy to you. Okay, so next we'll take different. We'll take the again in the next class we'll take the same rectangular function with unequal duration. So now we have taken with equal duration, both are duration is 2 2. Now next in the next class we'll take the rectangular signal with unequal duration. Say for example, one is having duration 4 and another one is having 2. Then we'll try to convolve the signal with the graphical method. Okay, then we'll see what kind of answer we are getting. Again, so now what we'll do, we'll try to solve this with the help of Laplace transform. We can also solve this with the help of Laplace transform. Okay, let me check whether we have solved it with the help of Laplace transform or not already. Okay, so this question only we are solving. Okay, with the mathematical approach, we got some answer. Okay, so we have not solved. Okay, so the same question we'll try to solve with the help of the Laplace approach. Okay, so then we'll get some idea whether the Laplace transform is working for equal for finite duration signals also or not. That we can verify now. So now the same problem with the Laplace approach. Laplace approach. What is the problem? This is x of t from 0 to 2, x of t. Then h of t is also from 0 to 2, h of t. What is the mathematical expression? X of t is equal to u of t minus u of t minus 2. H of t is equal to u of t minus u of t minus 2. Okay, then if you take the Laplace transform x of s equal to 1 by s minus e power minus 2s, e power minus 2s divided by s, h of s equal to 1 by s e power minus 2s divided by s. Again 1 minus e power minus 2s divided by s, h of s is equal to again 1 minus e power minus 2s divided by s. Okay, then we have to multiply these two to get y of s, because y of s is equal to x of s multiplied with h of s. Once if you multiply, you will be getting e power 1 minus e power minus 2s into 1 minus e power minus 2s divided by s square. Then you multiply this, you will be getting 1 minus 2 e power minus 2s e power minus 4s divided by s square. Then we are having three different term. Okay, we will separate it directly. Okay, so y of s is equal to 1 by s square minus 2 e power minus 2s divided by s square e power minus 4s divided by s square. Okay, now if you take inverse Laplace transform, again y of t is equal to t into u of t minus 2. Okay, again e power minus 2 is there, that means t minus 2. Okay, t minus 2 u of t minus 2, again here already minus is there. Okay, if e power minus 4 is not there, we can simply write t, but because of this e power minus 4, this will become like t minus 4 u of t minus 4. Okay, so now we got y of t. Okay, so just again this t into u of t also we can write like r of t. Okay, r of t, this entire thing we can write like 2 into r of t minus 2. This thing we can write like uh, uh, r of t minus 4. Okay, r of, I think we are making some mistake here. That is, once if you multiply e power minus 2s with e power minus 2s, you will be getting plus here. Okay, so again here also plus, here also plus, here also plus, again r of t minus 4. Okay, so now we got y of t. We'll try to plot this. Okay, y of t, then whether we get the triangular function or not. Okay, so y of t is equal to r of t minus 2 into r of t minus 2 plus r of t minus 4, r of t minus 4. Okay, again the same expression already, I think the same expression already we got in the mathematical approach. Okay, I think that you can verify with the previous video, the same answer we got in the mathematical approach. Anyway, we'll try to draw this. Okay, so first r of t, and you know that r of t goes from in general r of t goes from 0 to infinity with a slope 1. Okay, so it goes like this. Okay, so 0, but at t is equal to 2, what is happening, it will be going like this. Okay, at t is equal to 2, what is happening, one more line going with the slope minus 2. Okay, so this slope is minus 2, but for this slope the slope is minus 1. Now what will happen, both will add. Okay, once if you add the slope, again first we'll write this. Okay, so this is 0 2, then at 4 what is happening, you are introducing one more ramp with the slope of, with the slope of 1. Okay, so now once if you add these, all these three signal, okay, what you will be getting, okay, from 0 to 2 no problem, you can go comfortably with the slope value of 1. At exactly at t is equal to 2, what is happening, already slope 1 is there, this is with the slope minus 2, so you will be getting effective slope as minus 1, so that your line will go like this with the slope of minus 1. This is of slope minus 1. Now you will be going like this, but already one line is there here. Okay, now you are going with the slope minus 1, already one line is there with the slope plus 1, so that both will cancel, so finally you will not be getting anything. Okay, your diagram will stop here. Okay, so again you are getting the same answer. Okay, the triangular function. This is the triangular function y of t. Okay, thank you. Okay, next class we'll see some different example. That means rectangular function with unequal duration. Okay, so that question we'll try to solve with help of the graphical approach and also with help of the Laplace transform. Okay, and then we'll verify whether we get the same answer that we have already got in the previous mathematical approach.